Okay, welcome to Discovering Design with Chemistry, Chapter 1, Part 2. Today we're going to go over the second half of Chapter 1, starting with page 13, Scientific Notation. So we're going to talk about scientific notation, but first, let's review significant figures. Let's say you have this problem on a test. 8.197 centimeters times 12.2 centimeters equals 100.0034 centimeters squared. How many significant figures are in the first two numbers? Well, this one is 4 significant figures. 8, 1, 9, and 7 are all non-zeros, and so they are all significant figures. And then this one, 12.2, is 3 significant figures because 1, 2, and 2 are all non-zero figures, so they're all significant. So the minimum, though, is 3. So that means that we only report the answer to 3 significant figures. The problem is if we reduce it to 100, which has 3 digits, that's only 1 significant figure. So we need to have 3 significant figures. So how do we do that? The answer is scientific notation. In scientific notation, you only write 1 digit to the left of the decimal. So remember that we need 3 significant figures for the answer to our math problem. So in this case, we would write 1.00, because that way you only have 1 digit to the left of the decimal, but you also have 3 significant figures because any zeros that are at the end of a number and to the right of the decimal are significant. So then you multiply the number by 10 to an exponent, or as we say, to a certain power. So in this case, we would write 1.00 times 10 to the second power. What is 10 to the second power? That is 10 times itself, or 10 times 10, which is 100. So you're basically saying 1.00 times 100, which is 100. But because you wrote 1.00, you have 3 significant figures, whereas if you just wrote 100, you would only have 1 significant figure. So let me clear the drawings. So let's practice this a little bit more. How do you convert 5,007 meters to scientific notation with 3 significant figures? So it's going to be 5 point something because there can only be 1 digit to the left of the decimal point. You need 3 significant figures, so it needs to be like 5.00, right? Wrong. You also have to round up because the last figure is a 7, so it becomes 5.01. Then how much do you multiply it by? Well, to turn 5 into 5,000, you have to multiply it by 1,000, which is 10 to the third power. That's because 10 to the third is the same as saying 1, 2, 3, right? It's the same as saying 10 times 10 times 10, which is 1,000. So another way to look at it is you just have to move the decimal place 1, 2, 3 spaces, and so that's the third power. So we're going to try another example. The Earth is about 94,402,000 miles from the sun. So we're going to convert that into scientific notation. We can only have 1 digit before the decimal point, so that's going to be 9 point something. We also only want 2 significant figures, so that makes it 9.4. Then we're going to multiply it by how much? Well, to make it simple, we'll just count all the figures after 9. So 1, that's 10. That's there's going to be 7 because 1, 2, 3, 4, 5, 6, 7. So 9.4 times 10 to the 7th, which is 10 to the 7th is the same as 10 times 10 times 10 times 10 times 10 times 10 times 10, which is 10 million. But again, you can make it super simple by just counting how many spaces to move the decimal. And in this case, it's 7, 1, 2, 3, 4, 5, 6, 7 spaces. So you're going to multiply 9.4 times 10 to the 7th power. So before we move on, we're going to do one more. We're going to convert 0.000004713 liters to scientific notation with 3 significant figures. So just like with the other numbers, we take the first significant figure and put a decimal after that. And the first significant figure is 4. And we want 3 significant figures, so it's going to be 4.71. And then by how much do we multiply it? It's actually very simple to explain how to do this. You just count how many spaces you're moving the decimal point. In this case, we're moving it 1, 2, 3, 4, 5, 6 decimal spaces. And since we're going to the right rather than to the left, we're going to make it 10 to a negative power. And in this case, since we moved it 6 spaces, that's times 10 to the negative 6th power. That's the same as saying 1 over 6 tens, or divided by 6 tens, or multiplied by a negative 1 million. But either way, all you have to remember is that you simply move the decimal space and you count how many spaces you had to move it. So again, in summary, in scientific notation, you only put 1 digit to the left of the decimal, and then you multiply it by 10 to an exponent or power. So this is the sort of thing a fella ought to know. You might have a test question in this chapter and multiple test questions in future chapters that require you to put your answer in scientific notation in order to have the correct number of significant figures. So now we're going to talk about derived units. A derived unit is a unit of measurement obtained by multiplying or dividing units. So if you multiply a unit times a unit, that gives you units squared. For example, centimeter times centimeter equals centimeter squared. Squared units measure area, for example, length times width. However, centimeter times centimeter times centimeter is centimeter cubed. Cubed units measure volume, which is length times width times height, or depth or thickness. So we're going to practice this concept a little bit. My brother has a huge fish tank. It's about 5 feet long, 2 feet wide, and 3 feet tall. So we're going to calculate how much water we need to fill his fish tank. So first we're going to convert the measurements to centimeters. We know that there are 12 inches in a foot and 2.54 centimeters in an inch. So we're going to quickly convert each of those measurements from feet into centimeters. So we have 5 feet, 2 feet, and 3 feet. We're going to multiply each of those by 12 inches over 1 foot, and then by 2.54 centimeters over 1 inch. The feet and inches cancel each other out, and we get these answers. But there are 3 significant figures in our original measurements, so we want 3 significant figures in our answers, which is 152 centimeters, 61.0 centimeters, and 91.4 centimeters. The next step is to multiply the measurements. So 152 centimeters times 61.0 centimeters times 91.4 centimeters equals 847,460.8 centimeters cubed. But again, we can only have 3 significant figures, so that makes it 847,000 centimeters cubed. So that's the volume of the fish tank, and that's how much water we need to fill it up. But what is cubic centimeters in the real world? When you buy milk, you usually buy gallons or half gallons, and when you buy large bottles of soda, you know, that's like 2 liters. So what is cubic centimeters in the real world? So measurements for liquid volume include gallons in the English system and liters in the metric system. Before we move on to figure out how many liters of water we need to fill my brother's fish tank, let's talk about measuring liquids. So we typically measure liquids using a graduated cylinder. How many milliliters are in this graduated cylinder? So here is the meniscus, which is the bottom curve of the water. And usually the curve is downward, but either way, you always measure at the bottom of the meniscus or the bottom of the curve of liquid. Also, you have to be sure to bend down to look at the meniscus so that the meniscus is at eye level. This is the sort of thing that, you know, a fella ought to know. So in this case, we're calling it 6.6 milliliters. So you're not going to have a test question like about the meniscus or a test question that requires you to measure a liquid correctly, but you will have to measure liquids very frequently in this class for your lab reports. So we already learned in the first half of chapter 1 that inches and centimeters have predictable relationship because they're both length measurements and they don't change. Like an inch is always an inch, a centimeter is always a centimeter. And so you can test that relationship and predict exactly how many centimeters there are per inch, or how many inches there are per centimeter, and the same is true for volume measurements. So we're not going to conduct experiment 1.2, which is, if you're following along in your book, page 17, but we are going to talk through it. So in experiment 1.2, we're supposed to determine the volume of a container in cubic centimeters by measuring the length, the width, and the height, and multiplying those numbers by each other. Then you fill it with water, so you know exactly how many cubic centimeters of water there are. Then you pour that water into a measuring cup marked to milliliters, and then you calculate the relationship. So how many cubic centimeters are in 1 milliliter? 1. So this is super simple. 1 cubic centimeter equals 1 milliliter. This is the sort of thing a fellow ought to know for test question purposes, because you will have test questions that require you to convert between cubic centimeters and milliliters. Now we're going to talk about about converting between volume units. So in general, converting between volume units follows the same rules as converting between length units. For example, if we want to convert 5,261 milliliters to liters, and we know there are 1,000 milliliters in a liter, we simply multiply by 1 liter over 1,000 milliliters. The milliliters cancel each other out, and the answer is 5.261 liters. But what if you start with something like cubic centimeters and you want to convert it to liters? So we know that there are 100 centimeters in a meter, but if you start with a cubed measurement and you want to convert to another cubed measurement, you have to use a cubed conversion fraction. So for example, let's say you want to convert 3.820 cubic meters to milliliters. We know 1 cubic centimeter equals 1 milliliter. And so a simple way to calculate it is to just convert cubic meters to cubic centimeters, because then we can just say, well, however many cubic centimeters we have is exactly however many milliliters we have. So it's super simple to just convert it that way. But that means that first you have to convert the cubic meters into cubic centimeters. So we'll write out our equation, 3.820 cubic centimeters times 100 centimeters over 1 meter. However, we have to cube the conversion fraction as well. But what does that mean? So when you cube something, you're multiplying it by itself 3 times. So 100 cubed is 100 times 100 times 100, which gives us 100 million. And for 1 meter, 1 times 1 times 1 equals 1. So there are 1 million cubic centimeters in 1 cubic meter. So we're going to rewrite our equation, 3.820 cubic meters times 1 million cubic centimeters over 1 cubic meter. The cubic meters cancel each other out, and the answer is 3,820,000 cubic centimeters. But we're not done. There were 4 significant figures in the original measurement of 3.820 cubic meters, but there are only 3 significant figures in 3,820,000 cubic centimeters, because non-zero numbers are significant, but zeros are only significant if they're between 2 non-zero or 2 significant numbers, or they're at the end of the number and to the right of the decimal. So all of these zeros, none of these zeros are to the right of the decimal, and they're not between other significant numbers. So none of those zeros are significant, but we need 4 significant figures. So how do we do that? We convert it to scientific notation. 3.820 times 10 to what power? So because we're moving the decimal space 1, 2, 3, 4, 5, 6 spaces, that's the 6th power. So 3.820 times 10 to the 6th milliliters, or cubic centimeters, which is the same thing. By the way, this is the sort of thing a fella ought to know. Remember, when you're converting a cubed measurement, to always cube the conversion fraction. And the same is true for squared measurements as well. If you're converting a squared measurement, always square the conversion fraction. So we're going to go back to the fish tank. We wanted to know how much water we need to fill a fish tank that's 5 feet long, 2 feet wide, and 3 feet tall. We calculated it to be 847,000 cubic centimeters. So we're going to convert that to milliliters. Since 1 cubic centimeter equals 1 milliliter, I'm just going to rewrite it as 847,000 milliliters. Since we started with centimeters, we don't have to do a cubed conversion, but we did just convert between a cube length measurement, 847,000 cubic centimeters, to a volume measurement, which is milliliters. So now you know the volume of water you need to fill the tank, but what is 847,000 milliliters in layman's terms? Let's say you have a 2-liter Coke bottle, and you're going to use that to fill the fish tank, and so you want to know how many times you're going to have to fill that bottle up. So how many milliliters are in a liter? 1,000. So that equation will tell us how many liters we have. So 847,000 milliliters times 1 liter over 1,000 milliliters equal, but that we're not done with that, because that tells us how many liters we have, but we have a 2-liter bottle. We want to know how many bottles it's going to take, so we have to also multiply it by 1 bottle over 2 liters. So in other words, we're going to divide it by 2. So the milliliters cancel each other out, and the liters cancel each other out, and the answer is 423.5 bottles, but again, we only want 3 significant figures, so 424 bottles. So let's say you don't have a 2-liter bottle. Let's say you have a gallon milk jug. So we're gonna start the same way by converting to liters. 847,000 milliliters times 1 liter over 1,000 milliliters, and there are 3.7854 liters in a gallon. So we're going to multiply it by 1 gallon over 3.7854 liters. The milliliters cancel each other out, the liters cancel each other out, and that gives us 223.7544 gallons. But again, we only want 3 significant figures because we started out with 3 significant figures. So we're going to reduce that to 224 gallon milk jugs to fill the fish tank. So remember what we talked about in the very beginning of chapter 1. Matter takes up space and has mass. When we measure the amount of space something takes up, we're measuring the volume. When we measure how much matter exists in something, we're measuring mass. For example, liquid matter has more mass than steam, which is water in gas form. And we're going to learn more about measuring mass later, so don't worry if you don't really understand it yet. We'll get there. Now, an important thing to remember is that mass is not the same thing as weight. Mass measures how much matter is in something, but weight measures how much gravity pulls on something. So if you put an object somewhere where there's very little gravity, say on the moon, it's going to weigh less than it does on Earth where there's more gravity. Similarly, if you put it on Jupiter where there's more gravity, it will weigh more even though it has the same mass. So we're going to watch a video about the difference between mass and weight. Oh, crap. Messing up. Okay, so the sound was off. We're going to start it over with the sound on again.
Our sun is massive. My New Year's resolution is to lose weight. We use these words and phrases practically every day, but what is the difference between mass and weight? The answer is extremely simple, but most people don't actually know what it is. Let's get the scientific physics definitions out of the way first, then we'll discuss what they actually mean in normal people terms. Mass. Mass is a physical body's resistance to acceleration when a net force is applied. Okay, what does that mean in normal people terms? First things first, a physical body is just a fancy name for a collection of matter or stuff. So a physical body could be a planet, a galaxy, a vase, or a puppy. Whatever. Next, acceleration is just a fancy way to say how quickly something changes its motion. And last but not least, a net force is just the entire force affecting this collection of matter. So we could rewrite the definition of mass to say how much a collection of stuff can stop itself from changing its motion when something else is trying to move it. That makes more sense, right? So then what is weight? According to physics, weight is the force exerted on a body by gravity. Normal people terms, please. In other words, the Earth is constantly trying to pull everything near it down towards its center. That's how gravity works. And the more mass or stuff something is made of, the more stuff gravity can pull on. Therefore, the stronger the force of gravity gets. So using our two normal people definitions for mass and weight, let's think about an example. Imagine a semi-truck parked in front of your house. Now imagine trying to push that semi-truck down the street. Basically impossible, right? But why? Most people would say it's because the semi is just too heavy, which refers to its weight, but that's not totally true. Actually, the semi simply has too much mass, or is made out of too much stuff. And you pushing on it, aka the force acting on it, is simply not enough to change its motion. So the semi's mass makes it difficult to push down the street. But now imagine if somebody told you to lift the semi-truck off of the street. Also virtually impossible, right? But why? The semi-truck, a recognizable collection of mass or stuff, is constantly being pulled to the center of the Earth by gravity, which is considered to be its weight. So your attempt to outdo Earth's gravity by lifting the truck away from the Earth is truly an attempt of lifting the semi-truck's weight. Now think about this one for a second. When you visit other planets, you're always made of the same amount of stuff. Your mass never changes, but every planet you visit has different gravity, so your weight changes. You can check what your weight would be on other planets at astronomate.com. So what is the difference between mass and weight? Mass is simply how much stuff or matter something is made out of, and therefore how hard it is to move or change its motion. And weight is how much that collection of mass or stuff is being pulled down by the force of gravity. So now you know the technical difference between mass and weight. And as a result, you are officially smarter than most human beings on planet Earth. Now go forth. Push and lift something made from a lot of stuff resting on a table at a dinner party and officially become the most interesting person in the room. Booyah!
Okay, if that video didn't work, like if you couldn't hear it, the URL is at the bottom of the slide, so you can look it up and watch it separately.
We love science.
Okay. So, since mass is the amount of stuff that's in an object, the mass doesn't change based on where you are, on Earth, in space, on the moon, on Jupiter, etc. But because weight is a measure of how much gravity pulls you down, it changes based on where you are. In fact, even on Earth, your weight can change based on where you are. So on the very top of a mountain, you weigh less than you do at sea level. Interestingly, your weight also goes down when you get closer to the center of the Earth, such as going down a mine shaft, because there's less and less gravity closer to the center of the Earth. If it were physically possible to be in the very center of the Earth, you would have equal pull in all directions, and so you would weigh nothing. Mass is typically measured in grams and kilograms. There's also an English unit for mass called slug, but we won't actually measure anything in slugs in this class. There is a test question that includes slugs, but it tells you exactly how many kilograms are in a slug, so you don't have to memorize anything about slugs for test purposes in this class. All you have to know is how to set up the basic unit conversion calculation that we've been doing a lot of in chapter 1. Normally 1.00 milliliters equals or measures 1.00 grams. We'll usually use grams in this class, not kilograms, because we're going to be measuring relatively small amounts of things. The metric unit for weight is newtons. Just FYI, you can figure out your weight in newtons by converting your weight from pounds to kilograms and then multiplying your weight in kilograms by 9.807, and that's how many newtons you are. So for example, 130 pounds is 59 kilograms, which is 580 newtons. But just FYI, you don't have to know anything about measuring or calculating newtons for any of the tests in this class. So again, mass is a measure of how much matter exists in an object, and weight is a measure of how strongly gravity pulls on an object. This is the sort of thing a fella ought to know. You might have a test question asking you to write out the definition of these terms. When measuring time, we use seconds. The second is a metric unit, which means you can record it or report it in kiloseconds, seconds, milliseconds, etc. However, if you're timing something, say, in order, like the amount of time it takes one substance to react with another substance, and you're given a measurement that is, for example, 1.5 minutes, you need to know how to convert that to seconds in order to complete your calculations and report it appropriately. So you probably already know this, but you do need to know that there are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. So just for fun, we're going to do a quick unit conversion problem. So how many kiloseconds are there in a day? So we start out by writing out 1.00 days. How many hours are in a day? 24. How many minutes in an hour? 60. And how many seconds in a minute? 60. So the days cancel each other out, the hours cancel each other out, the minutes cancel each other out, and that gives us 86,400 seconds. And we started out with 3 significant figures, and we have 3 significant figures, so we don't have to change that at all. But we're not done. The question was, how many kiloseconds are there in a day? So we're going to convert 86,400 seconds into kiloseconds. Based on the fact that it says kilo, and we know that kilo means 1,000, you can probably guess that there are 1,000 seconds in a kilosecond. So we're going to multiply it by 1 kilosecond over 1,000 seconds, or in other words, divide 86,400 seconds by 1,000 seconds. Seconds cancel each other out, and we get 86.4 kiloseconds in one day. We started out with 3 significant figures, we ended with 3 significant figures, so we're good. Another unit of measurement is density. Density tells us how tightly packed matter is. For example, which is more dense, liquid water or water vapor, or in other words, steam? So liquid water is more dense. The equation to calculate density is mass divided by volume. And since we usually measure mass in grams and volume in milliliters in chemistry, density is usually recorded as grams divided by milliliters, or grams per milliliter, in other words. So let's say you're given a brick of some unknown metal. You know it's a metal because it's shiny, but you don't know what metal it is. So you measure the brick and you find that it's 1.00 centimeters wide by 1.00 centimeters thick by 4.00 centimeters long, and it measures 10.84 grams. So we're going to calculate the density. We already know the mass, which is 10.84 grams, so first we'll figure out the volume. And how we do that is very simply 1.00 centimeters times 1.00 centimeters times 4.00 centimeters, which gives us 4.00 cubic centimeters. That's the same thing as saying 4.00 milliliters. So then if density is grams over milliliters, then it's very simple. Just put 10.84 grams over 4.00 milliliters. So we're dividing 10.84 by 4.00, which gives us 2.71 grams per milliliter. And since we start out with 3 or 4 significant figures, because 4.00 has 3 significant figures, then our answer needs to be 3 significant figures, which it is, so we don't have to change it at all. So that's the answer, is 2.71 grams per milliliter. By the way, sorry. So this is the sort of thing a fella ought to know. You might have a test question that requires you to calculate the density of an object. Density is an extremely important unit in chemistry because each substance has its own density. So if you calculate the density of something, you can determine what substance it is. So we determined that our unknown substance has a density of 2.71 grams per milliliter. So using this table, you can figure out what substance it is. And the answer is aluminum, because its 2.71 grams per milliliter is closest to 2.70 grams per milliliter, which is the density of aluminum. Story time, boys and girls. So Archimedes is credited with using density too wisely in a story that dates back to the 200s BC. Because it was first recorded about 300 years after it allegedly happened, it may or may not be true, but it's still an interesting story. So King Hiero II ruled Syracuse, Sicily in the 200s BC. He ordered a crown to be made from pure gold, but he suspected the goldsmith had cheated him and added some silver to the crown to save money. He hired Archimedes to find out whether the crown was pure gold or mixed. Back then, they knew that gold had its own unique density, so it was a fairly simple matter to just calculate the density by dividing the volume from the mass, and then see whether the density of the substance matched the known density of gold. In fact, you may recall an example in your textbook, which if you're following along, it's page 23, where they explain that fool's gold has a density of only 4.9 grams per milliliter, while gold has a density of 9.3 grams per milliliter. So if someone gives you a lump of gold, or what they claim is a lump of gold, you can calculate its density and then determine whether it's really gold or just fool's gold. But in this case, the crown had a very complex shape, so Archimedes wasn't sure how to measure the volume of the crown. So how was he going to determine the volume? The Roman architect who first told the story said, "The solution which occurred when he stepped into his bath and caused it to overflow was to put a weight of gold equal to the crown and known to be pure into a bowl which was filled with water to the brim. Then the gold would be removed and the king's crown put in its place. An alloy of lighter silver would increase the bulk of the crown and cause the bowl to overflow." So Archimedes figured out what we now know, that you can use water to calculate the volume of irregular objects. Since silver has a lower density than gold, it takes more silver to create the same mass. Gold's density is 9.3 grams per milliliter and silver's density is 10.5 grams per milliliter. So if we have a 100 cubic centimeter lump of gold or silver, how much mass will it have? So we're going to read out the equations with the information we have. We have 19.3 grams per milliliter, or 10.5 grams per milliliter for the densities of gold and silver, and we know that we have 100-gram objects. What we don't know is how much volume they have. So I'm not going to go into the math behind this because we don't have the time to do that right now, and you should have had it already anyway in algebra. But the answer is that 100 grams of gold is 5.18 milliliters, or cubic centimeters, and 100 grams of silver is 9.52 milliliters, or cubic centimeters. So you can see that 100 grams of silver takes up more space than 100 grams of gold. Therefore, a 100-gram mixture of silver and gold would also take up more space than 100 grams of pure gold. So Archimedes' solution was to weigh the crown and then get an amount of pure gold that weighs the same as the crown, and then put the pure gold in a bowl and fill it with water. Then take the pure gold out and put the crown in. If the crown was a mixture of gold and silver, and a certain weight of silver takes up more space than the same weight of gold, then the crown would have more volume than the pure gold and it would cause the water to spill over. According to later versions of the story, Archimedes was so excited that he forgot to get dressed when he jumped out of the bathtub and ran naked through the streets, shouting, "Eureka!" which means "I have found it." That probably didn't happen, but nevertheless, Archimedes was the first to realize that we can measure the volume of any irregular object by measuring the amount of water it displaces. The Archimedes principle states that a body immersed in water experiences an upward force equal to the weight of the water displaced. Very basically, that means that if you put something in water that is more dense than water so that it sinks, it will displace, or in other words, push away some of the water. No duh, right? So, but we're going to talk some more about this principle. Let's say we need to determine the density of an unknown substance, but it's an irregularly shaped object, and so we can't determine its volume by measuring length, width, and height in centimeters with a ruler. Remembering the story about Archimedes, how would we determine the volume of this substance in cubic centimeters? So recall that 1 cubic centimeter equals 1 milliliter. So to determine the volume in cubic centimeters, you can use milliliters. So first, you fill a graduated cylinder partway with liquid such as water, and then you put your object into the liquid, and you subtract the original volume from the new volume. So let's take a closer look at this picture. In this case, we filled the graduated cylinder to 50 milliliters. Then we added our object, and the new measurement is 75 milliliters. So we subtract the original measurement of 50 milliliters from the new volume, which is 75 milliliters. 75 minus 50, which gives us 25 milliliters, which is the same as 25 cubic centimeters. There's no test question asking you to calculate the volume of an irregularly shaped object, but you will do so in experiments throughout the class, so you need to know how to do this. Although the Archimedes principle tells us that objects displace water based on their volume, it says more than that. One very important concept to understand is that less dense substances float on top of more dense substances. No. So for example, the density of water is 1.0 grams per milliliter, and the density of ice is 0.93 grams per milliliter. That means ice is less dense, so ice floats in water. This is the sort of thing a fellow ought to know. You might have a test question asking you whether a certain substance will float in something else. So let's practice this concept a little bit before we close out this chapter. We're going to calculate the density of olive oil. So we'll say we measured the mass of 495 milliliters of olive oil and found it to be 455 grams. So again, how do we calculate the density? So we'll calculate 455 grams over 495 milliliters, because density is grams per milliliter, which means you simply divide the grams by the milliliters. And that gives us, whoops, went the wrong direction, 0.919 grams per milliliter. So recall that the density of ice is 0.93 grams per milliliter. Will it float in olive oil? The answer is no, it will not, because ice is more dense at 0.93 is a higher number, therefore more dense than 0.919. And so the ice will not float in olive oil, it will sink. So now we're going to look at orange oil. Let's say you measured 329 grams in 379 milliliters. So we're going to rewrite that 321 grams over 379 milliliters, which equals 0.847 grams per milliliter, and that's the density. Mineral oil, let's say you have 566 milliliters, you weighed it, and you found it to be 472 grams. So we're going to calculate that also. 472 grams over 566 milliliters equals 0.834 grams per milliliter. So that's how you calculate the density. So now that we know the densities of these oils and the density of water, which is 1.00 grams per milliliter, we can predict which ones will float over or sink in the others. So let's say you pour 10 milliliters of each of these liquids into a 50 milliliter graduated cylinder, and then you walk away and give them enough time to separate from each other. Based on what we know about their densities, which one will sink to the bottom? So water is 1.00 grams per milliliter. That's the heaviest. That's the greatest density. So that's going to be on the bottom. And then next is olive oil at 0.919 grams per milliliter. Then orange oil at 0.847 grams per milliliter. And finally, mineral oil at 0.834 grams per milliliter. Lastly, you remember that ice has a density of 0.93 grams per milliliter. So where is it going to float? The answer is, since 0.93 is less than 1.00, but it's higher than or larger than 0.919, it's going to float on top of the water, but under the olive oil. So now we're going to throw some solid objects in there, and we're going to see whether they float or sink. Leather is 0.86 grams per milliliter, so where is that going to float? The answer is on top of the olive oil, but under the orange oil, because 0.86 is less than 0.919, but greater than 0.847. The balsa wood is going to float on the very top, because this is 0.13 grams per milliliter. Raw pigeon peas at 0.84 grams per milliliter. This one's actually, it's so close that it may or may not float on top, but we're going to say that it does. It's going to float on top of the orange oil because 0.84 is less than 0.847. Cocoa butter at 0.9 grams per milliliter is going to be right alongside the leather. It's going to float on top of the olive oil, but under the orange oil, because 0.9 is less than 0.919, but greater than 0.847. And then finally, sodium, like give you a small piece of pure sodium, it's 0.98 grams per milliliter. So where is that going to float? And the answer is right alongside the ice, on top of the water, but under the olive oil, because 0.98 is greater than 0.919, but less than 1.00. However, if you know anything about the chemistry of pure sodium and water, you'll know that sodium and water tend to react with each other quite violently, even bursting into flame. So it probably would not be a good idea to throw a piece of sodium, pure sodium, into this this little graduated cylinder that you've got, because you know that it's going to sink all the way down to the point where it's touching the water, and then you're going to have a violent reaction, and you may end up with shards of glass all over the place that you have to clean up. So the last thing we're going to do is watch this video, which illustrates this concept.
So I have this aquarium, and it's got water in it. Now, I'm going to take this brass weight, and I'm going to put it in the water. And you know what's going to happen. It's going to sink into the water. Sinks all the way down to the bottom. However, if I take a cork and put it in the water, it floats in the water. Now, why does the brass sink and the cork float? Most people will say, well, it's because the cork is lighter than the brass. And that's true to a certain extent, but there's something else that's important as well. And to understand what's important, I want you to first look at that green tape that's down there. Notice that it's roughly at the level of the water, okay? That's important. So, I'm going to now take this bowling ball, and it's a heavy bowling ball. Right? It's a heavy bowling ball. And I'm going to put it in the water. Now, will it sink or will it float? Watch the level of the water relative to the green tape, and watch what happens to the bowling ball. It doesn't sink. It floats. Why? Well, notice that the water had to rise as the bowling ball sank in it. That's because the bowling ball takes up space, and so it has to push water out of its way. So the water level goes up because the bowling ball is pushing the water out of the way. Well, it turns out that this bowling ball doesn't weigh as much as an equal volume of water. So it doesn't weigh as much as the water that it displaces. Since it doesn't weigh as much as the water it has to displace to sink, it can't sink. It floats. In other words, this bowling ball is less dense than water. If it's less dense than water, it floats. That's really why the cork floats. The cork is less dense than water. If it's more dense than water, like the brass, it sinks. So whether or not something sinks or floats depends on its density. I have another bowling ball, and it's heavier. And when I put it in the water, it sinks. So in the end, these bowling balls have the same volume, but their weights are different, their masses are different. So in the end, their densities are different. The blue bowling ball is more dense than water, so it sinks. But this bowling ball is less dense than water, so it floats. We'll end this with two common items, a Coke and a Diet Coke, 12-ounce cans. Is there enough difference in these two products to see a difference in the way they float or sink? And the answer is yes. If I put Coke into water, it sinks. If I put Diet Coke into water, it floats. Why? Coke is sweetened with high fructose corn syrup, and it takes a lot of high fructose corn syrup to sweeten Coke to the taste everyone expects. So when I add up the masses of the water and the Coke syrup and the carbon dioxide and the high fructose corn syrup and the metal of the can and so forth, and then divide by the volume of the can, it's slightly more dense than water, so it sinks. However, Diet Coke is sweetened with aspartame. It takes only a tiny amount of aspartame to get the same level of sweetness as a lot of high fructose corn syrup. So there's less mass in this can. Mostly it's the mass of the sweetener. And the total mass of all the contents and the metal of the can divided by its volume is slightly less than the density of water, so it floats.
So that's it for chapter 1. You'll need to do a lab report on experiment 1.3, and you also need to turn in your comprehension checks and chapter review questions. And I'll also have to complete your chapter 1 test. And remember that one of your parents has to put their initials in the top right corner to verify that you took the test closed book. And that's it.